Section 2.4 deals with the shapes of distributions. The distribution of a data set tells us the values in the data set as well as how often they occur, or the proportions. And the distribution can be described using a table or a graph or a formula, and we've seen that before graphically when we looked at histograms and other things. So here we have in figure 2.10 a histogram. We're looking here at the heights of some female college students, I believe. And one thing to notice about this distribution is that it seems to be symmetric about somewhere around 64.5. In figure 211, we see examples of distributions where the mode is different. And when we're looking at a continuous distribution as we're described here, the mode essentially refers to the hilltops. So in A, we only have the one hilltop. And then in part B, there's obviously two sort of hilltop points. And then in part C, we have like three hilltop points. So in part A, that's unimodal, and then B is bimodal, and C is multimodal. In figure 212, we see symmetric distributions, and then part A is sort of a bell-shaped distribution, which is very similar to the heights of the female college students, the example we looked at earlier. And then they also give us a triangular distribution and a uniform distribution. In contrast, figure 213 shows us skewed distributions. And we have right skewed and left skewed. So to remember which one is which, just look at the side where the tail is sort of stretched out more, and that indicates the side of the skew. So with part A, you can see that the tail is on the right side, and then with part B, it's on the left. Figure 214 is what we call a reverse J-shaped distribution. We probably won't have much opportunity to work with this, except if we ever look at the exponential distribution, which I don't think we do in this class. In figure 215, we encounter the relative frequency histogram for household sizes. This data was taken from current population reports, which is published, which is a publication of the U.S. Census Bureau. And we see from this histogram that the data has a skew to the right. And remember that the population is the big set about which we desire to know more. If there is a sample, which usually there is, then that is a subset of the population, which we hope is a representation of the population, which we hope is a microcosm, like a mini-me version of the population. And so anyway, population data is the values of a variable for the whole population, and then obviously sample data is the values just for the sample. So also we can differentiate the population distribution, which again refers to all of the data, as opposed to the sample distribution, which only refers to the sample data. And so our hope is that the sample distribution does a good job of mimicking that of the population distribution. So in figure 216, we see the population distribution for U.S. household sizes, and we see 6 different sample distributions. And so our hope is that when we draw a sample, again, we want it to be representative or have the same characteristics as the population. So just looking at those 6 sample distributions, just ask yourself which one seems to do the best job, which one matches the most closely, and which one is maybe not so good of a sample. And remember, whenever we draw a random sample, any one of these samples of whatever the size is, as well as any of the other samples of this size that are not included here, those would all have the same chance of being selected. So when we do statistics, the idea is that from a probabilistic point of view, most of the samples do a decent job of representing the population, and only a few of them don't. And that's essentially what is being addressed here in key fact 2.1. And notice that this is kind of obvious, but the larger the sample size, the better the approximation tends to be.